Yeah, so I think maybe a good kind of place to start talking about is like what kinds of, what is modeling, and what are the reasons we do it. And like if you, the very simplest, there's kind of like two extremes for what you might want to do. One is to predict things. So you're just predicting y that you want to know from x, and maybe you have several x's. And you just basically pick whatever variables x correlate with y, and you stick them into the model or correlate somehow. There's kind of always the famous thing that just because something correlates doesn't mean that it's necessarily related. I like this. This is kind of fun. The various correlations. So they're spending on science versus how many people hang themselves. Which I don't know. This one is good.
I like that.
I don't know, maybe. Per capita cheese consumption, number of people who died by becoming tangled in bed sheets.
Interesting.
I did not know that was a thing. Although that's a lot of cheese, though. 30 pounds of cheese a year.
I look at the death by bed sheets going on.
It's a lot of deaths. Like it's 800 people a year.
That'd be an embarrassing way
That's
to go.
a bad way to go. I mean, you're comfortable, but yeah, I don't know. Maybe. Age of Miss America murders by steam. I'm not even sure how you can murder someone by steam, unless they work in a train. Oh yeah, well there's like six, yeah. But they're very correlated. Yeah, this is like correlation 98. How many game arcades and science doctorates? The more sociologists we have, the more things we launch into space. Civil engineers and mozzarella consumption. Yeah, so there's kind of all these wacky things. So I mean, this is just kind of for humor, but in a very real sense, like a lot of the time it's very like you'll have like a whole bunch of things that you think might be important and or could be used for prediction. You just stick them into the model, and especially when you have many of them, and you kind of cherry pick what's useful, and which is a bad thing to do because you're kind of basically data mining and p hacking. But okay, yeah, you find things that are correlated, whatever. There's of course nothing mechanistic about it, so this is everything that the AI machine learning things are talking about. And the reason that really sucks, or can really suck, is anytime the future is not like the past. So one example is you have your x observations are like from 0 to 10. Okay, so what happens if x is 15, right? You have no past observations of what happens under those conditions, so you have no idea what y will be. And then, just kind of the relation, even if it's like just a really simple linear model, the relationship between x and y can change to like the slope of it. Usually these models, like machine learning is, it'd be way more complicated than, a linear model. We had Disney colleagues getting excited about stupid math height, or I don't know, computer science type things. But they'd say something like temperature and then number of salmon, and I was like in a working group, someone did this, and here's the data are kind of noisy, they're all over the place, and so they said they took this model and they said, oh look, this looks really great, like this model explains so much, and the model looks like this. Like, yeah, but we don't think that it's actually this, do we? Like, are you kidding? So yeah, and then so anything that And well, this is, a ridiculous case of overfitting, but if things like change a little bit, like you'll get predict completely the wrong answer. So these things are nice, but anytime the system changes, it falls apart. So you want to have a little bit of, some biological reasoning and mechanisms. At the other extreme, there's we're just kind of modeling processes that everything that's underlying Y, like all the things that affect the population. And often when we do that, we kind of ignore how well we're actually predicting the thing that we're modeling, which, sometimes is okay. Like, anytime I do theory and like we usually use a very simple model, we use just a couple of processes, and that's just for building intuition, like how does density dependence interact with, when you have predators, things like that, it causes cycles. So in that case, it's perfectly fine, but we're not predicting anything, we're not explaining anything. But then there's also kind of applied biologists that go out and try to do this. They love their system, and so they write down everything that they think is important, and that number of things. If a mathematician does that, they'll write down like 2 or 3 things. If a biologist writes it down, they're going to have like 50 things. And the problem is everything you write down, you have to pick a function of how change in that will affect Y, right? So you have to find data from somewhere that was probably taken from a different system, or very often there is no data. And so you have to like kind of guess at a lot of things, even when there's data on everything. And you have, right, so you have like how many foxes you have versus how many clutch size for the foxes, how many babies each mom has. And then you have things like how many foxes you have, and what the disease prevalence is, right? And so even if you have great data on that, there's still going to be a lot of variability in there. So there's, for a given number of foxes, there's going to be some number of babies on average with a lot of variability around it. And there's going to be some level of disease with some variability around it. The problem is unless it's all like in the same and very, very detailed study, you'll have no idea how a deviation away from in the number of births will correlate with a deviation away in the numbers, right? So you have variance in each of those, but you don't know how those two variances are related. You don't know the covariance between births and disease, right? And as you get, and you can have a covariance between every combination of 2 things that you're modeling. So if you have 30 processes, that's 30 squared things you have to estimate, even if you're only looking at pairwise things and not so yeah. And this is, it's funny because like in the 60s, when we just got some computers that could simulate things, we said, oh, let's stick everything that we can possibly think of in a computer model and simulate it, and we're gonna, just like the physicists have it with the solar system, we're gonna perfectly predict ecosystems. And it failed miserably. Like it was called the International Biological Program, and it was even the Soviet Union and the US collaborating on this. And it failed very miserably, and everyone got very depressed. And for some reason, people still try to do this, like 60 years later. Like, so yeah, there's this very persistent belief that if you have the right mechanisms, you'll be able to predict things, and you won't. And you also won't be able to kind of really know what's important either. So usually what we're usually trying to do is try to balance these things. A lot of it is kind of very implicit. For example, you'll see a lot for linear models, people will try to predict, plant productivity from precipitation. Okay, that's reasonable, maybe. But a lot of the time we kind of don't really have an idea of how things will change. But the point is, you're just kind of really focusing on a few important processes that you think from prior knowledge, and this isn't like explicit in any way in terms of uncertainty, but you try to focus on things that you think are going to be important. Yeah, so basically by fitting and there's like different kinds of that. So there's that example where you just choose a few things to go into your linear model. There's this example, this model of kelp that I just showed you, where I'm kind of very carefully finding the right equation, and then I let the data tell me what the parameter values are. I'm just kind of fitting it to data. But there was it took me 2 years to find the right equation. for this. And I don't know if it's the absolute right one, but I've checked almost all the other easy ones. But the really cool thing with that is then you can compare different models that have different mechanisms in them and see how well they explain their data. And that's kind of a way of hypothesis testing, right? So for this, if you've heard of like Planet 9 that we might or may not have in the solar system, there's like a big debate. Supposedly maybe there's a planet way far out there that we can never see because it's so far away from the sun. But if it is there, like it can explain all the wacky deviations and small deviations in planet orbits that we haven't been able to up to this point. So there's like two big camps and there's no data, so no one's right. But that's how, that's how physicists infer, right? So in biology, there's a very old idea of if you want to prove causation, you have to do an experiment. Which is fine unless you're working with a very complicated system like gut microbiomes, and like it's very, very hard to tease things apart because there's millions of pairwise interactions that could be going on. And B, with the thing that we're doing with fisheries, like you can't do experiments at all, right? But doesn't mean you can't know anything, right? The physicists can't do experiments with planets either, and they're fine. Like they never move a planet or move a black hole and see what happens. So yeah, so we kind of want to try to be in between those two extremes and I think that's where ecology needs to go more, being less black box, but also being less kind of made up models. And with a lot of the with an ecology, a lot of the more powerful things that we can do, and we really want to get at interactions of how really do things work, what causes what. The most kind of powerful thing I think are time series. And the reason we kind of have to think about it in a time series framework, so how things change from one time to the next, is that the past can affect the future. So with the simplest case, how many baby foxes we're going to have next year is going to depend on how many moms we have now, obviously. But then there's a whole bunch of other things. So, the first one is like everyone thinks about that, of course. But then maybe having too many foxes is bad. Maybe it's not. Maybe it leads to disease or competition. Maybe having too few foxes is actually very bad. So if you have too few, they actually go extinct for a whole bunch of reasons. Yeah, and there can also be kind of these long-term effects when you think about interactions with other species. So having a lot of foxes now, maybe that means there's going to be a lot of the eagles are going to do very well, and then 2 years from now, all those baby eagles will grow up, and then there's going to be a lot of predators. So there's these kind of complex lags, and some of them are between species, some of them are within species. So there's a lot of systems that have these very big predator-prey cycles, and so a lot of people try to find out why. And so for one of them in Canada, I think it was the rabbits and the lynx, maybe. It's either that or like the voles and something else. But why is there huge population swings in number of voles that you have? And everyone said, oh, it's because you have too many predators, and the predators also kind of go up and down. So everyone thought it was a predator-prey cycle. But it turns out that when you have a lot of predators around, the moms are really stressed out, and so and there's kind of like a transgeneration thing where if the mom is really stressed out, then her kids won't have a lot of babies, right? So and the predators were just they were part of the dance, but they were really just crashing when there's not a lot of food and going right. So it's not like they were eating all that much. It's just these like delayed maternal effects. So yeah, there's a ton of stuff that could be going on with these kinds of dynamics. So there's we're usually focusing on the abundance of something, and so we're tracking that population. And so if we start writing down models for this, okay, exponential growth dynamics there are very simple, either it's exploding or it's crashing. That's the first idea. If I want to try to model the second idea, which is like a little bit of competition, then we use this kind of model. So abundance next year is abundance now times some growth factor, and also times 1 minus n. So if n is at 1, that's as abundant as they can be. But if you're close to that, so the closer n is to 1, then this whole 1 minus n factor goes down to 0. So you have very small population size next year, right? So that's the simple way you can do density dependence. And so we said, this is in ecology, we said like in the 60s, this is a reasonable model of populations. So let's see what can happen here. And it turns out quite a lot. So you can kind of go up and play with this yourself. But this is kind of nice. So what this is doing is, so this is this is population abundance on the y over time on the x. This is how many we have to begin with. If you move the slider around, you use different initial conditions. And then this slider is that population growth factor. All right, so if it's small, then the population just grows. So this is just how many babies does each mom have in a year? Or actually, I mean, there's no moms and dads; they're all reproducing. But yeah, so if it goes up, you have more critters. But then if you go up a little bit more, you start getting these overshoots, and you have this cycle, right? So, and this is like a period 2 cycle. So here in this year, things were very good, but there's so there's lots and lots of critters, but there were so many critters that there's not enough resources. So everyone's having few babies. So next year the population goes down. Now conditions are good, and next year everyone has more babies, right? So that's kind of the idea of what's going on there. But if you keep cranking this up, you go flips a few times. Now you go to like this. So this one we call the period 2 cycle, because you're here, then you go up, and then you come back in 2 years to the same value. This jumps up to a period. Well, this is this is already big. Let's see, it's surprisingly tricky to find these because it's on a narrow range. One of these is so this is a period 4 cycle, right? So we're here 1, 2, 3, 4. So it takes 4 years to go around the cycle. Then things get a little bit kind of more complicated, right? This is still a regular cycle, but it's 1, 2, 3, 4, 5, 6. Right, so it's always a multiple. Should go in multiples of 2. And then if you keep kind of cranking up, this looks like complete randomness. And some people would. So this is basically chaos now, but it's chaos in the mathematical sense that it's perfectly predictable if you know exactly the initial condition. But if you don't, then it looks like a complete mess. But it's following the rules exactly. It's just that kind of one iterative thing. There's no uncertainty or variability here at all. And so just kind of explain this one, and then you can watch the other video. That one's like 20 minutes long. But let's see where this starts. Oh yeah, let's just explain what this is showing with these kinds of diagrams. So what this shows is on the x, now that's the lambda that we were looking at, and on the y is the densities of population, the population abundance that you see over time. So when growth rate is very low, so this lambda is very low, it was kind of like a flat line. So when we saw, eventually we only just saw one value of population abundance. When we made lambda bigger, it went back and forth between 2 values. So you see the 2 here, then it became 4. So you see 4 lines here. And the whole thing, if you plot every possible level of population growth, you get this kind of what we call a bifurcation diagram. Right, so it looks kind of like this, right? So you get no cycles, period 2 cycle, period 4 cycle, 8, and then it keeps getting more complex. Eventually, with this cloud of points, you get that as chaos. And what's really cool is that if you kind of look at, you start here, like that's that map that we were just looking at, and you keep zooming in on one part of this map. It's you see the same pattern coming out, the same period doubling blowout happening in every little bit of it. and this is a fractal. All right, so we've already got chaos and fractals, and this kind of basic idea that you go through period doubling. So 1 to 2 to period 4 to period 8. That's the characteristic route that all dynamical systems take as you approach chaos in the parameter regime. So right away, this was like ecology really motivating mathematicians to do a lot of new cool things. But the point here is, all I'm kind of saying is that with this very, very simple model, we barely considered anything at all, and we already have like a giant mess of what can happen in terms of the dynamics. So this we kind of went over, but kind of what I want to point out here is that what happens isn't entirely random. So if you have like this period 2 thing, regardless of where you start, you always end up in this period 2 cycle. You can start at a low population size or a high population size, but you always get pulled into that period 2 cycle. Or you get pulled into that period 4 cycle, or you get pulled into that chaos regime, right? But it never goes to 0. It never explodes to infinity. It always stays in that spot, right? And so that's kind of the idea of an attractor, that we have this long-term behavior. It might not be, very easy to predict. It could be chaos. It could be something. But we have this long-term behavior and this kind of area of, range of population sizes or area. So, or area and kind of state space where the system always tends to stay or come back to. That's why we call it an attractor. So it attracts things from different initial conditions. So it's stable in that kind of broad sense, right? So ecosystems can have attractors, so that was kind of a simple one where you just have one species. If you have 2 species, then this is kind of that example of a predator-prey cycle. To make things a little bit easier, we kind of just like we did with the logistic map, we kind of crunch down time. So we collapse if you collapse these graphs along the x-axis over time, you just kind of lump them up. You plot, and instead you plot how many predators you have versus how many prey. You get this kind of circle. It's this kind of cycle that the system goes around. So it's just another way of seeing it.
How long does it take, like, if someone were to model that, to know that their model was like correct? Correct in the sense that, like,
between a few years and never.
Yeah.
Between a few days and never. Yeah, so I mean, and you can have different models having the same performance, right? So sometimes you can't even tell what the right one is. And you always need like kind of a lot of data to be more confident. I think, I mean, these are a lot. I mean, the links here are actually a very nice system. So they actually are, they look kind of like this. But a lot of systems that, I work with, it's incredibly noisy. Yeah, and so, but if you kind of collapse time away, you can see very clearly it's kind of an attractor, and I keep getting this wrong, but like, yeah, I'd say 2 dimensions. Some people say technically a circle is 1-dimensional, but anyway, so this is kind of a bigger size. We can get to 3 species and kind of a 3-dimensional thing where this is now a model where you have predator-prey, but also the producer modeled here. So we have 3 things. So it's just, this is the model of a food chain. And so when you have that, this is what the dynamics look like if you plot kind of the 3 species against each other. And this is called a teacup attractor. Can you see the teacup? Or okay, yeah, it's upside down. Mathematicians get very excited when they give something a name they think is clever. And they call this one the butterfly attractor. And this is from a model of one of the very simple models of the atmosphere. So kind of actually finding, so chaos is very hard to study mathematically. And so we kind of stumbled on it a few different times. So once with the populations, this was like kind of one of the very first examples that was, continuous time differential equation system. This was Lorentz in 1968. So he published that paper as like, here's this weird thing going on that is completely unpredictable. And what the hell, and everyone kind of ignored it for 4 years, and then people realized, oh, it's this really, really cool thing in math, and now it's like one of the most cited papers. that was completely ignored for a while because no one knew what to do with it. And what that kind of, that kind of connects with weather a little bit. So here's another one of those plots where we have, we can change lambda. But one thing we can do here is, so this is now plotting actually two populations. They both started this, so in red and in gray, and they started almost the same initial population abundance, but slightly different, slightly tiny differences in population, in initial population size. Okay, so and as I crank up, and this is still like in a regular regime, so let's go a little bit crazier, right? So as I crank this up, right, you see this is smaller. On the left, all the points are on top of each other, but on the right, the red and the gray dots are starting to separate, right? So, and this is the same, the only difference in these is where they start. And so initially they are right on top of each other, but gradually they get worse and worse. And actually the difference grows exponentially, right? And so this is the reason why we'll never be able to have decent weather forecasts, because weather is a chaotic system. That butterfly attractor, I mean, that's kind of the very simplest model of it. But unless you can perfectly measure everything about where the atmosphere is at any given point and then model it, and you can't measure it perfectly, your forecast is always going to be bad. And because it's exponential, so this is the mathematical definition of chaos, is exponential deviation of deviations grow exponentially. What that means is that if we get 100 times better at measuring what the conditions of the atmosphere are right now, we'll be able to forecast 3 more days into the future. We'll get like 15-day forecasts. So even if we pour a ton of money onto this, like it's never gonna work. So that was a few kind of distractions, but those are all the things we learn about math and the broader world from biology sometimes. But okay, so let's get back to like ecology, and where you kind of want to understand how things work. And so, for example, if we have, again, we want to know how many foxes there's going to be next year. If it just, let's say it's like the simple case, it just depends on how many foxes we have in the past, with all of these different kinds of things that could be important, right? So maybe there's a bunch of these things that could be important, and we're going to find out what their role is. Okay, so foxes only depend on foxes. And if we have a time series of foxes, we can, write down a dynamical model and fit it to data on foxes, and fit the parameters, see if it works well, etc. Great. We could also do this if, if foxes are interacting with rabbits and we have data on foxes and data on rabbits. It's basically the same thing. Okay, so that's fine. Now, one of the really, bad news is that ecosystems have more than one species. So this is actually the ecosystem where we have data that we're working with data from. But that isn't it. That is horribly simplified. This is what you showed to third graders. This is what you showed to slightly more mature ecologists. But this is still horribly simplified. But already this is way too much, because the other terrible truth where this entire thing falls apart is that we only really have time series on just a few species. So yeah, it's like fisheries, things we track. We really aren't tracking all the different zooplankton, all the little tiny animals that fish eat, or the algae, or anything about the ocean, how it moves. So, and usually almost all, like, this is the data set we're working with is actually kind of amazing because of how many species it has. Usually you just have like 1 or 2 species. Like with giant kelp, I only have kelp. I don't even know how many urchins there are, because it's very, very hard to count urchins. Kelp you just see from a satellite, but urchins you have to go and dive, and that's very hard. So the kind of models that the whole thing is called empirical dynamic models. It's kind of a buzzword, but one of the things that we usually do in them is to work to reconstruct the attractor. Okay, and so the whole premise here is that we have some things, and let's just stick to like foxes and rabbits, right? Say we have data on foxes, we don't have data on rabbits. We don't know, we have no idea what the rabbits are doing in terms of abundance. Okay, so and then if we want to predict foxes next year, we're kind of screwed because we don't know what ZT is. But if we kind of rewrite ZT, right? So we take this first equation and we just change the time indices. So ZT, if we just kind of copy and paste this here, then that must have been y at t minus 1 and z at t minus 1, right? So that's what ZT is. And now we can take this and plug it into here. Okay, so now we get this thing where this thing, this g is what ZT is, right? So now we have yt plus 1 is a function of foxes now and foxes last year and rabbits last year. We can do the whole thing over again, plug in for this ZT minus 1. So now we have an equation for foxes next year as a function of foxes now, foxes last year, foxes 2 years ago, and rabbits. And then we can, kind of keep packing it until you're kind of getting pretty close to the dynamics of the foxes as a function of just past abundances of the foxes. So you basically lumped in the dynamics, everything that's happening with the rabbits into the past lags of the fox abundance. Okay, so that's kind of the little bit mathematical version of how you see it. The more visual, again, with the butterfly attractor, is this thing. So
there's a very powerful theorem proven by
yeah, so I mean we can skip this, but if you're ever talking to mathematicians, you tell them Tauken's theorem. And if you're talking to
series shown Hictions. For example, consider the 3 times series shown here. These are all copies of each other. They are all copies of variable legs. Each is displaced by an amount tau. So the top one is unlagged, the second one is lagged by tau, and the blue one at the bottom is lagged by 2 tau. Tarkin's theorem then says that we should be able to use these 3 time series as new coordinates and reconstruct a shadow version of the original butterfly manifold. So let's see how this works. This is the reconstructed manifold produced from lags of a single variable, and you can see that it actually does look fairly similar to the butterfly attractor. Each point in the 3-dimensional reconstruction can be thought of as a time segment with different points capturing different segments of history.
Plotting lags of x, different lags of x.
The reconstructed manifold is then the library or collection.
And what we get is something that is
legs. The reconstruction.
Yeah, it's just exactly. Yeah, it's abundance 2 years ago, 3 years ago, right? And we plot them against each other. We get this thing on the bottom, but it's exactly in every way we care about. It's analogous to the original thing where we plotted the 3 variables against each other, right? So even though we don't know 2 of them, we can use lags of just one of them to reconstruct it. And you can keep going with this, if you can have as many dimensions as you want. The only problem is, that how noise will affect things and whether you have a long enough time series. But the whole key point is with all of this, the only thing I want you to kind of take away from this is that by using lags of past population size, we're basically, this is the whole, this Tauken's theorem, the attractor reconstruction idea is the reason why we can say we're really implicitly capturing the effect of all the interactions with all the other species, with all the other variables as they matter to this species. Okay, so it's, so there's kind of a deep mechanistic connection there in terms of what is going on. So it's not just, we're really modeling the dynamics as opposed to something, just based on the past and completely black box, even though we don't know what those key things that it's interacting with are per se. We can, if we have data on them, we can ask that. And then, we talked about this, we use E number of lags. And so how do we determine that? We just try models with every possible E and we look at which predicts best. So that's very simple, but that, I don't know, that might be something. Well, you guys are pretty good with for loops, so I might let you guys do that on your own. Yeah, you have a call to the function that fits the EDM, and then you just repeat it for different E's.
Would this be considered like recursive then if you're just calling like the previous
Yeah, I think so. Yeah, you're just kind of, yeah, you're winding up, but there's a limit to how many you need. And usually E is not very big. And the other thing that is good to point out, so E is the number of dimensions you have, right? How many lags, right? So, but how many data points do you need? So like if E is 1, right? And so you've got like 10 data points, then if E is 1, right, it's just a one-dimensional thing, and you have 10 data points, that's a pretty good sampling of what's going on. If E is 2, now 10 data points, they're a little bit farther apart, right? If E is 3, then you're not sampling very well this volume, right? So usually you want something on the order of, so if you have a time series length n, you want to have E less than least square root of n. I think there might be like a -1 or something here. But the point is, yeah, if you set the embedding dimension way too high, then you're just basically overfitting, because you don't really have any idea of where things go in the state space, because it's just uncertainty.
What is n?
N is the length number of years. So how many years of data you have? Yeah.
So you can almost consider that to be like the dimension or like.
Yeah, it's sort of the dimension in which things take place. The attractor dimension is a little bit more particular thing, but I think I loosely called it attractor dimension to keep things a little bit simple. Yeah, so typically E is going to be not very big, and largely because we don't have many years of data, right? So we have 30 years, or like, so 25 squared of that is like 5 minus 1 is 4, right? So we generally won't want to go past E is 5 or 6. Okay, but anyway, so if that's all we need, we just predict foxes next year from past abundances of foxes. This is something we can actually do very easy with autoregressive models that you watched the video on. Right, all you do is plot foxes next year versus foxes now, foxes next year versus foxes last year, and versus 2 years ago, and you fit those regressions. Okay, so you can do that. You can also, and if you don't want to do linear, you can do Gaussian processes, which let you basically estimate the function that's not linear. Whatever, that doesn't really matter. For our purposes, we don't really care about what those are. But the whole idea is you're predicting next year from the last 3 years. And so the whole index thing here, we're kind of really focused on the time. So every data point, how it, what predictions it affects depends on what portion of the time series it's in, right? So for example, these 3 points will only ever be used to predict, so this point will only ever be used to predict this point, and that point. That's it, because we're indexing by time. Now this is actually kind of bad because we could be using more data points. For example, this went down, but the same thing happened here and here, right? So we could be using more of the data. But also if you have noise and there's kind of a shock to the system and you have like a big die-off, now there's very few foxes this year, but last year and 2 years ago there was a lot, right? So you're kind of using the wrong things to predict next year. And so what we actually want to do is look at predict foxes next year based on not time lags per se, but based on how fox abundance changed the last time the whole system was in a similar state, right? So we were on the same part of the attractor essentially. Right, and so this is the other key thing, is that we want to predict foxes next year from nearby points on the attractor. This is the way that it's better than our models, just autoregressive stuff. And so we need kind of an index of where a data point is in terms of their location in state space. Okay, so let's say, so before this, if we have like for each observation, we call the abundance in the year 2000 as n2000. And the thing, if e is 1, the thing we can predict from that is 2001, right? So it's just nt plus 1 versus nt. But if we have a dimension of 3, then we use, to predict 2001, we use 2000, 1999, and I screwed this up. I think it should be 1998. Oh, I just didn't iterate that, yeah. Yeah, so we used 2099 and 98, right? And so the whole thing, so, and by the way, every time we fit this model, we fit nt plus 1 versus nt in that kind of linear regression. So every data point, once is being used as a predictor, once is being used as a thing we're predicting. With E of 3, we each point is a predictor 3 times. But anyway, so you get this kind of regular structure of lags that we just reshuffling the time series data for predictions. But yeah, so anyway, when we do this, like in the case when we're using 3 lags, every observation, like this one, number 5, abundance in 2004, it now has like 3 things associated with it: abundance in 2004, abundance in 2003, and abundance in 2002. So those 3 numbers are going to be our set of coordinates, right? So it's like if you have coordinates in x, y, and z, that's our coordinates in this case, 3-dimensional space. Okay. And so every point every data point now has a set of 3 coordinates. So what we can do is measure distances between points in state space. Okay, and we can do this for all different points, and we call this distance I. And now when we kind of regress, this yt versus yt plus 1, we can do what we're saying a basically weighted regression. So we have this, so the farther points are apart, the less, so we're predicting a certain point, and we're asking for this other data point that we have, what's its influence on this data point? Okay, the influence is going to be less if it's farther away on the attractor. Okay, so then we have this, then the weight is exponential minus distance, and then times this kind of scale metric that we fit. Okay, so if theta is big, then distance is going to have a very big impact. If theta is 0, then it doesn't matter how far away it is on the attractor. So all points are weighted equally.
Distance, is that distance between each other?
Yeah, between those 2 points. Yeah. So it's this pairwise distance in this coordinate space. Yeah, so now that we have that, so we have this parameter theta, this new thing that's showing up. And actually, we're going to have a new theta for, well, again, this example was 3 lags, so population size now, and another theta for population size 2 years ago, and 1 year ago, and 1 for 2 years ago. And so those thetas can be different. For example, with this one, it's going to be bigger because there's like a nonlinear thing. Right, so basically, the bigger the theta is, the more wiggly this function that we estimate is going to be. I screwed up writing this here, so this was supposed to be theta of 0, and in this case, it's just kind of flat. It doesn't matter what abundance last year or 1 year ago was. It's just a constant kind of contribution. And then 3 years ago was this theta should be lower, and so that's kind of more of a linear effect. Okay, so that's how that idea of distance on the attractor weighs into when we're building these actual models, right? In this case for fluxes, this would be our full model, right? So abundance yt is yt plus 1. Abundance next year would be this plus this, like all of these 3 things added up together. If we don't have any interactions on top of each other. Okay. Now, one thing you might notice is if theta is big, then the model is quite wiggly. It's quite complicated. It means it really matters how far away points are on the attractor to the effect. If theta is 0, it's basically flat. Okay, and actually, when we do any kind of autoregressive models, it would be like, as you saw in the video, it's like xt plus 1 is some coefficient times xt plus that intercept. So there's always kind of like a fixed effect or a fixed term. And so this term would basically get lumped into that fixed effect. So essentially what this is saying, when theta is 0, the predictor doesn't matter, right? Because it doesn't matter what the density was last year. And this is what we call kind of automatic relevance determination in this thing. So theta is like a hyperparameter that we fit, but if it ends up that the best value is 0, then we're basically throwing out this predictor from the model, and that helps us reduce overfitting. So that's kind of a handy way. There's more fancy things you can do, but that's what we'll use. All right, now there's 2 more things where we should note. First is 2 important things in what we'll be doing. First is, this example we had was predicting foxes next year by adding up the effects of this year, last year, and 2 years ago. We just add all these effects together, given for a given value of yt, yt minus 1, yt minus 2. Just add the values of the red lines together to get yt plus 1. So we have basically 3 predictors here, 3 lags of population size. But we can also have other predictors such as environment in addition to population size. So it's not just population interacting with itself. There's also the forcing of, for instance, climate. So we might have, for example, temperature and 3 lags of temperature as predictors as well. We might have ocean climate indices, etc. So it's the exact same thing as we've been doing before, but instead of just past abundance, we're also going to have past temperature, for example. So it'll be another predictor. And the other thing to note is that we'll be building spatially so spatial models, spatial extension of these models. So instead of having just yt and yt minus 1, so abundance of foxes over time, we'll have abundance fish over time and at different latitudes. Okay, so instead of just one vector over time, it's a matrix. So over time, and the columns, for example, are different latitudes. And we'll fit a spatially hierarchical model where we say our default assumption is that all locations follow the same set of curves in the models, the same dynamics. But we have this parameter that says, an extra parameter that says how different how much the curves differ among different populations. And so then and we fit that. So our default assumption is that all populations are doing this, responding the same way to environment and abundance, but maybe they don't. Okay, and so what we can do is quantify how much they don't follow all the same rules. So how much ecosystem interactions, responses to temperature vary across locations. And then, but if they don't change much, then what this allows us to do is basically crank up the sample size, because yes, we have, for instance, 30 years of data, but now we have 30 years of data across 8 locations. Okay, and to some extent, those are independent samples in the model. Okay, so just to show you a little bit of what is going on here, let's look at some examples of what these models look like. And I think I showed them at the beginning, but let's see. Results, plots, 23 effects of environment. Here's a really simple one. The E is 1. That's a different species. We'll get to that in a second. Here's a really simple one. So there's only lag 1, and we have population size. So it's like foxes last year, or predicting foxes next year, predicted by foxes this year. Okay, so foxes this year would be on the x-axis, and then this is the effect. And the different lines are different populations of, in this case, Dungeness crabs. So how much current Dungeness crab abundance affects next year's abundance in different locations. Okay, they're all kind of doing the same thing. But then we have the other, and it's just one lag. But then we have the other 3 predictors here. These are indices of ocean climate out in the Pacific Ocean. And so North Pacific Gyre Oscillation Index, that's like think of it as a set of seasons that last for 12 years instead of 1 year on land. So yeah, so the cycle goes through about every 12 years. And you can see, depending on where you are, depending on which population it is, a NPGO level of 0, an index of 0, can have very different impacts and can be a good thing or it can be a bad thing for how many crabs we have. This is the El Nino oscillation. This is the Pacific Decadal oscillation. These are all indices of ocean climate. Okay, so this is the actual model that we have, right? So population size next year is going to be whatever level of population size is now, whatever NPGO is now, whatever these two are now. Find the curves, find the location on the y-axis for each one, add them together. That's our predicted population size next year. Okay, so that's what's under the hood in these models. Okay, here's another one. These are blue crabs out on the East Coast. So across rows, again, we have different predictors: population size, winter temperature, precipitation, and how many crabs are being caught in fisheries. And then here we have, instead of E of 1, we have E of 5. So we have 5 lags. Okay, with the foxes, we had 3. With the Dungeness crabs, we had 1. Here it's 5. So here's across different 5 lags. Each of these predictors gets a potentially an effect at each lag. And then you can see some of these are very wiggly. That means there's a big effect. For example, if precipitation 3 years ago is quite important, it's very wiggly. Obviously, with the top left here, population size last year. So the more blue crabs there are last year, the more blue crabs there will be this year. That makes sense. You'll see a bunch of these are flat, as we pointed out in discussion. And that's because the model tends to want to select a phi of 0. Okay, so if there's not much of an effect of anything, it's going to say, okay, the phi is 0. There's no effect of this driver at that lag. Okay, and that's why a lot of the lines are flat. It tends to bias towards flat lines, which is another way of saying there's no effect. Doesn't matter what the winter temperature effect is; it's always constant. Don't worry so much that they're different lines. Just worry about whether they're flat or not. Okay, so a bunch of them are flat. Some of them are really curved. The curvy ones are the which drivers and how many years ago they are important to abundance next year. Okay, the very wiggly ones, for example, winter temperature looks like very, very important for blue crabs. So that's how you kind of read some of these models. Here's like anchovies out in the West Coast. It's a little bit different. We have a bunch of drivers, only 3 lags, just like with the toy fox example. And then we can look at what kind of predictions do we actually get. Here's the blue crab database. The black are data, the blue are model predictions, and the blue shaded regions are basically the confidence intervals or the uncertainty intervals in the model predictions. Okay, so and you can see in this one, different locations. So each plot is a different location. Have very different dynamics. Here you have these cycles that they're going through. Here it's population level that's kind of stable. And yeah, so you have different places going through cycles at different times, for example. So that's a nice one where the fit is quite good. Here's another, again, comparing model predictions and observed data. So here's sardines. They had a boom, then they busted. That was kind of similar everywhere in the Pacific Ocean. Then yeah, so we can look at a bunch. I'm not sure which, I don't remember which ones look kind of good and are good examples. Escaped. I think one of the squids were better. Yeah, so I mean, yeah, you get a bunch of model predictions out, and it's very, very clear that sometimes different populations of the same species are doing very different things in different locations, and that's something that we want to quantify, and especially how different the responses are to things like climate across locations as well. But the main effect is how does climate affect the populations? That's our main goal, and the end of all this, broadly. So yeah. So those are the things. Let's put this all together. We're building dynamical models of time series. We're doing very fancy ones that you might be able to do in the future, hopefully. We're building, so with these empirical dynamic models, we're using a tractor reconstruction that lets us really implicitly account for the dynamic of unobserved species and environmental variables. So we're really kind of striking a really amazing balance between the all prediction, no mechanism, and the all mechanism, no good prediction extremes. We're kind of right in the middle there, what we started out with. So we're predicting things well, but we also have actual dynamical models that are capturing these really, really complex systems and what's going on in them. And in that way, this is better than autoregressive models that almost everyone uses for time series. They might use machine learning models, but it's the same set of stuff. It's still very limited, unlike this approach, often. And to account for nonlinear interactions, we use Gaussian processes. That's all you need to know about that. And that automatic relative, that theta parameter is quite important, so you would want to review that. Then we'll have spatially hierarchical models, again, just as I said, to quantify how affects how much the rules differ from place to place, how much the clockwork varies over locations and ecosystems. And then we're going to predict things. Environment is going to be one of the predictors, so we can quantify the effect of climate. Again, Gaussian process EDMs that we're using, they're very good at not just prediction, but also estimating uncertainty in model predictions. This is not something that a lot of approaches do well in. This is a Bayesian approach, which means we're kind of very agnostic about the form of model error. We're very good at seeing how noise and uncertainty in the environment interacts with the kind of intrinsic attractor, the dynamics here. So they're very, very good at doing forecasting and management.